So yeah, it's great to have you here, Jan. So I just want to introduce you first. Just give me a sec, please. So Jan Peters is a full professor for intelligent autonomous systems at the Computer Science Department of the Technical University of Darmstadt, and at the same time a senior research scientist and group leader at the Max Planck Institute for Intelligent Systems, where he heads the interdepartmental robot learning group. Jan Peters has received several awards. Just going to mention a couple of them. The IEEE Robotics Automation Society's Early Career Award and several paper awards. He received an ERC starting grant in 2015, and in 2019 he was appointed as an IEEE fellow. So very happy to have you here, Jan. And your talk is on learning robot skills from data. So now I'll handle it to you.
All right, thanks a lot. So I can share my screen? Yes, it does work. Okay. All right. You guys see my screen? Okay. No, do you see the wrong one?
Yeah, I see.
Yeah, we can see your screen. Yeah.
You see, this is really getting confused today. But, do you see the presenter view or the other view?
This is a presentation view.
Okay, so I got it now the wrong way around. Great. That's about.
No, I think this is the right view, isn't it?
Was it?
I think it was the right view. It was the correct view.
Okay. Alrighty, so I'll just leave it like this then. Okay, so what I basically, but it doesn't show you the video. Does it show you the video?
Yeah,
You
it is showing the video.
Yeah. Mauricio, I don't hear you.
Yes, I can see the video, yeah.
Sorry, of course I don't hear you. So what you see here is a very, very old vision. Basically, it starts right at the beginning of robotics. And right after the first robot was ever built, they released this video as a commercial. And they claimed that this monster would in the future be, well, in our homes. Now, obviously, are the smaller versions. Now, by today, we have much nicer robots. We have done a lot in terms of good robotics, but actually we haven't come any further in the way we want to create robot tasks. Society has totally changed, since you'll see in a moment how anachronistic this feels, the futuristic robot scenario, while at the same time you see this family living in a 1960s scenario. In 1969, they were so certain it would just take a few years and everybody would have the household robot. So that brings us in robotics, obviously, under, well, some form of pressure, since it's been now 50 years. And 50 years later, we are still not capable of delivering the futuristic dream of robotics. It's despite literally all of the progress that we have had. And in the end, the key reason behind it is that today it's as difficult to create this task as it was back then. Sure, more people can do it, there are rules and so on, but programming up this, hacking up this robotics scenario, well, you would use very, very similar methods to 1969. You would use very similar control algorithm generation, and all of these things will be well, you can do it with undergraduate students today. You don't need a specialized engineer, but that's pretty much the biggest difference you have in terms of intelligence. There is very, very little difference. And this brings us, of course, to one question, that is, well, why have we actually failed in this scenario? Why have we failed this scenario? Why haven't we provided these robots? And then you look into where robots have been successful. And it's obviously, first of all, the car in the history. You wouldn't have a car manufactured in Europe if it wasn't for robots. And neither in the United States nor in Japan. This would be all in very poor country with manual labor otherwise. But instead, we have robots which are accurate to 150 micrometers, which follow precisely the same trajectory all the time, and everything is arranged such that the whole factory has basically zero uncertainty at the task. Then you look at the other two examples of robots which have been massively used, which is, well, robot lawnmowers and robot vacuum cleaners. And, well, robot lawnmowers typically have the wire leading them along, telling them which is the end of the lawn, and then they do a randomized algorithm between these boundaries, or they just follow a wire on the ground. And the Roomba, on the other hand, well, just runs against walls and then turns by a random angle. And everyone who's had a Roomba knows the first thing you do is you adapt your complete environment to the Roomba, and you remove all the furniture where it could potentially get stuck. So what do we do in robotics? Well, we typically adapt the task to the robot instead of adapting the robot to the task. And this, to some extent, because of the robotics environment, the robotics community, actually having, well, basically a classical engineering background. And while in a classical engineering background, you really avoid statistics, you really avoid modeling uncertainty. Since if you need statistics in physics, well, you've done a bad physics experiment, as Rutherford once put it. So we obviously need somewhat different, when we talk about learning in robotics, we don't talk about, well, supervised learning, but we really talk about scenarios like this here, where, well, there is a robot and we program it because it's built to mimic the human muscles, and we have to actually have it figure out how to generate the gait such that it actually works. Well, one way of formulating this is obviously by reinforcement learning, but you need very, very specific methods, and you need to be, well, somewhat you need to work really for the scenario, for the robotic scenario in this case. So it's slightly different than, let's say, in data science. So what we really we want to optimize the scores of the teacher. Oops. And we want this ways. One way is we want to do it by imitation, by learning from demonstrations, and the second way by learning from experience. And in the first part, let me skip this. The first part, we're just trying to reproduce the policy of the teacher, where we really, in this case, try to reproduce path distributions, so where we can fall back actually on, well, kind of an active supervised learning, where we generate trajectories to match the teacher's trajectory. But we need to nevertheless generate them actively and adapt only the, well, policy parameters this in there for reproducing the trajectory distributions. And here's an example of that, actually fairly dated. All the videos somehow have their sound turned on today. What you see here is a ball bouncing scenario with the ball and the robot is being taught to, well, bounce the ball. We actually thought this was a super difficult task, and it's super difficult because we totally failed at doing it with classical robotics methods, but it turned out that our imitation learning algorithm learned it on actually just one afternoon. Now, if imitation learning was always enough, well, in this case, we all could go with the PhD from primary school into academia. Instead, obviously, we need this painful self-improvement, which you see, for example, when which you see in motor skills, for example, when you're doing something like, let's say, you learn tennis, and the teacher takes you by the hand, and he shows you this is a front, this is a backhand, and you still take several hundreds of trials before you can execute the first forehand and first backhand properly. It's actually the motor control part is quite the hard part of the task. And that's obviously in the domain of reinforcement learning. where what teacher writes is on score. And in this case, we don't have access to the path distribution, but only to the path rewards. This makes our problem substantially harder, since unlike before, we no longer have access to the true distribution, and we have this real problem that we have to execute these things on the real system. If we could actually build a perfect simulator for a robot, robotics would be solved. Since if you can build a perfect simulator, planning methods from classical robotics could solve all the problems you want to. Reality is that humans need really, really good strategies, or have really, really good strategies. And these strategies are learned by, well, millions of hours of trials, and they include a lot of shortcuts. We know on what to focus. We know on what to, we know that catching a ball does not mean just extrapolating where the ball will be and create a physical model of the ball and then predict precisely where the ball will go. But it actually just requires one feature. That is where your ball is on the arena if you look, and when you're, for example, running backwards in order to catch a ball. That's it. Humans appear to have this huge set of bags of tricks. When you have these bags of tricks actually in robotics by human insight, you can become really, really good. But how can a robot get them? In the end, a robot can only get them by learning on the real system. So we have a somewhat harder problem here, that we want to max the return of the path generated by this path distribution, which we don't know. And well, that basically means there is no intuitively easy approach. Just taking off the shelf machine learning, reinforcement learning algorithm, this is not doing the job if you want to work with it well. So few trials that your robot can actually survive the scenario. And we figured out at some point that one of the smartest ways comes actually from human learning, that when humans learn from their own set of trials and in iterated decisions and problems, humans attempt to match not the best taken action, but the reward-weighted frequencies of their actions and outcomes. And that can be translated roughly as, can't we just create better policy matching the reward-weighted previous policy? In a sense, that just means we do success-driven self-imitation. And well, how would this work? Well, you would basically try to collect the successes. In this case, only symbolized for state actions here, in a single action scenario, a single time step scenario. You would try to capture the density of the good actions, but you would treat the reward like an improper probability distribution, so that you do not do something crazy, but you could actually start from a previous imitation. So this gives us a relatively simple problem, and it has resulted in, well, we introduced it very early on, and it's now resulted in most of the state-of-the-art systems which are applied in robot reinforcement learning. And it basically consists of just saying the obvious things, like we want to maximize the expected return, and we want to ensure that obviously we still have a distribution over the task. And in addition, we want to trade off the information loss over the past, over the past trials. And variations of this actually produce analytical solutions, including the Bellman equation and many famous equations, and have enabled us to get really effective algorithms for robot learning. They've resulted also in methods of our colleagues into like TRPO, for example. And the first time where we applied this was back, well, quite a while back, where we have now this scenario here, which you see here, where we teach a robot the ball and the cup movement, and by imitation learning. But imitations in this case fail because the robot has a 2-kilogram wrist. It doesn't have hand-eye coordination yet, and so obviously it only figures out, okay, I gotta move, and well, I get somewhat reward out of it. But after a few more trials, it figures out very quickly that the reward increases substantially if you, well, move a little bit more and insert more energy, and then it finally figures out that it needs to catch the ball, as you see here. And after about 90 trials, it actually becomes perfect. How does this compare to humans? Well, humans apparently, well, we did a small study on only relatives of my PhD student, and it appears to be that the 8 to 10-year-olds do not wish to learn it at all. The 10 to 12-year-olds already are somewhat better than this algorithm. We have by now way more efficient algorithms, just old videos, just so much nicer. Our newest algorithms can actually learn in 8 or 9 trials. They're better than the old algorithms, but they're slower than our newest algorithms. And grown-ups typically learn it in 3-4 trials. So it appears to be only me who took 3 months to learn this behavior. The surprising thing is that this year we my students to look again into well, what algorithm would actually do best, and it turns out that they're still all based on all the reinforcement learning algorithms, which are applicable in robotics, in which are capable of learning something like one-handed juggling with the 2 balls here, are still all based on this insight of relative entropy policy search. And what my student Kai Plöger, together with my student Michael Lutter, managed to show that you can actually learn than just episodes to do juggling with 2 balls at a quality level, which was super impressive. So it can actually juggle for half an hour without failing. And the surprising thing is it can actually even juggle blindfolded after having been trained insufficiently. This better here with every episode. So these are separate trial runs that you see here. And just to every single time it manages to after 20, 30 episodes, it's pretty much perfectly. It can juggling with 1 arm and 2 balls is actually super exhausting. For a human being, the comparable is actually to rather use 2 arms and 4 balls. And yeah, instead. So what we now increasingly obviously do is we compose with behavior using primitive behaviors, which we have just learned. And we put this together with context, learning execution, and many other things. And one of the things which interests us a lot is table tennis in this context. You can learn table tennis either, as you see here, with a combination of first imitation and then subsequently reinforcement learning, where Katarina has actually used the ball guns to train the robot. And I'm always saying she actually managed to managed to train the robot to become as good as she is. And it turned out that this is pretty much the limitation of the Barrett-Wham robot for table tennis. It does not actually get much better than that. The reason behind this is that the Barrett-Wham has a, well, 2-kilogram wrist. Now, I want to see you being nailed at the ceiling, trying to play table tennis, and while having a 2-kilogram weight in your hand put together with a racket. It's pretty damn hard. So my PhD student Dieter Büchler and I, we set out to build a robot. In fact, the first version of the robot was built 10 years back, and then before Dieter joined, and then later when Dieter joined, we actually figured out how to really make it work well. And what you see here is how the robot first trains, and it trains against a simulated ball so that we can really start from scratch. And we need quite a few hours of training against the simulated ball before we really before we really properly can actually hit a ball. But we accidentally typically hit a ball already. If you take a ball gun and you just aim at the workspace, you accidentally hit a ball after about 30-something minutes. And in the moment where the robot has has the first data points, it starts to zoom in. And while all the movement is done on the robot, the ball is only simulated in it because it's simply super exhausting to collect balls arriving every second. They wouldn't also be arriving every second if you were doing this with a human experiment. So the simulated ball, it goes on a simulated ball, these things still go much, much faster. But most importantly, the dynamics of this robot are so complicated that it would not be capable of learning, of being trained in simulation itself. It can only train to basically interceive a ball in the simulation. With subsequent training on the real system, it can actually become really, really good. And you look at this hitting behavior, this is both impressively good movement, but also impressively high accelerations. And well, we've just sent this out for publication. Okay, so it's obviously not all table tennis what we do. In fact,
John, sorry to interrupt, but we only have we are over time now, so maybe you can speed up a bit.
I'll wrap up. I have only this slide and one slide left.
Okay.
I thought I had 20 minutes, not 15.
It was 20, I think.
Yes, and I'm now at minute 15, so that's why I'm confused.
Oh, okay. Okay, thanks.
Okay, so I've actually planned in 2.5 minutes for questions. So it's not all table tennis what we do, quite the opposite. We actually know that industrial applications will require that we bring robot learning to industry. And well, Bosch basically at some point had a study where they told us, where they figured out that a product needs to be both expensive and produced in large numbers for robots to be applicable. And Manfred Gundel, former CEO of KUKA, basically said, present-day robots are made for repeating the same task thousands of times. Future robots will have to perform thousands of tasks several times. And I think this is also quite important. Assistive robots, companion technologies in hospitals, rehabilitation, as well as for the robot. With that, I'm pretty much at the end. I just want to say robot skill learning has a lot of implications for cognitive science, where we also work on, for classical robotics, and for machine learning. Here are some of the other topics where the methods from our world are being applied. I'll not go into detail, given that Mauricio wants me to catch up on time for you guys. So in conclusion, I hope I've shown you an interesting scope for how we can avoid all the possible scenarios and well, learn to adapt to the environment. I hope I've made the point. We have fairly efficient imitation reinforcement learning methods for anthropomorphic robots by now, and that our things can be reproduced on real systems, even in robot table tennis. With that, I'm at the end, and I hope you still have a few questions left.
Thank you, Jan. Are there any questions for Jan? So I see there is one question for you on the shared doc. Is the accuracy of on tracking in the table tennis case a limit of the simulation? This is the arm tracking and ball simulation limiting to this method?
Okay, so for the robot, for the Barrett WAM, you actually need to figure out a trajectory which is even executable at this high speed without breaking the robot. So it's actually the trajectory generation there already, which makes sure whether you, where tracking is not the problem, but if you have a good trajectory, but basically tracking becomes impossible, tracking control, if you have a trajectory. It's actually worse for our self-built robot arm, because there you could not precisely follow a trajectory, because it's built on insights from muscles. So we try to make it totally overpowered by taking two contracting pairs of muscles per degree of freedom, with the result that it can do catapult-like motion. But this catapult-like motion needs to be tuned for the actual trajectories. And you won't know precisely whether you're going to hit the ball here, here, or here. So you actually have to figure out how to make the system accelerate it up to the point where it could potentially hit the ball. But in order to stably steer it to some location, the learning system has to figure out how to decelerate in this complete region of the trajectory, of the ball trajectory, where the ball and the racket trajectory overlap. So the humans seem to be very, very good at this. So that in the 1990s, there'd been competitions on robot table tennis, and none of these things actually ever became really good. For the simple reason that despite that they had robots which moved faster than humans, moved more precise than humans, saw faster than humans, they actually built analog cameras for that to get super high accuracy of the ball tracking, both in terms of the precision of the cameras as well as the speed of the cameras. In every respect, they were 10 times better than humans, except for playing table tennis, where they were about 1,000 times worse, even worse than our robot, substantially worse than our robot, for the simple reason that they basically had not figured out what it actually means to be robust in such scenarios. Now, we hope to sidestep this question by, well, starting with the human trajectories if possible, and by doing learning where automatically only good solutions should survive.
Okay, thanks, Jan.